In the late 1960s, inside a Detroit scrapyard, a crane operator lowered a heavy steel claw onto the bronze roof of a functioning million-dollar machine. The public watched in horror as Chrysler systematically crushed 46 of its 55 experimental turbine cars, reducing them to scrap metal. This was not a recall of a failed product. It was the deliberate destruction of an American engineering triumph. Just a few years earlier, in 1963, Chrysler had handed 50 of these jet-powered coupes to 203 ordinary American families for real-world testing. The engine, which spun at an astonishing 500 RPM, required no antifreeze, had no pistons, no spark plugs, and could run on almost anything that burned. Drivers fueled them with diesel, home heating oil, kerosene, and even tequila. The paradox was undeniable. The Chrysler A831 gas turbine engine was a mechanical marvel that the American public genuinely loved. Yet the very company that spent decades perfecting it chose to annihilate it. But the real story of the Chrysler turbine is not only the story of crushed metal in a Detroit junkyard. It is the story of how the American auto industry tried to replace the internal combustion engine entirely, and the invisible forces that forced them to kill it. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, inside a Detroit engineering lab, in the years following World War II. In the late 1940s, the American sky was changing. The massive radial engines, piston aircraft engines with cylinders arranged in a circle around the crankshaft that had won the war were suddenly becoming obsolete. The aviation industry was shifting rapidly to the jet engine, a turbine engine that produced thrust by accelerating air and exhaust gases in a continuous, smooth rotation. Jets were faster, lighter, had drastically fewer moving parts, and ran on cheap kerosene instead of highly refined aviation gasoline. But on the ground, the American automotive industry was moving in the exact opposite direction. Detroit was permanently invested in the internal combustion engine, an engine that burns fuel inside its cylinders in a series of contained explosions to create power. To get more horsepower for the heavy, steel-bodied cars of the 1950s, automakers relied on massive V8s, 8-cylinder engines with cylinders arranged in two banks in a V-shape. These engines were powerful, but they were incredibly complex. A typical V8 had pistons, connecting rods, camshafts, and valves that violently changed direction thousands of times a minute. They required complex liquid cooling systems, exact ignition timing, and most importantly, an absolute dependence on high-octane gasoline. Inside Chrysler's engineering headquarters in Highland Park, Michigan, an executive engineer named George Hubner looked at the American garage and saw a mechanical dead end. Hubner believed the piston engine was fundamentally flawed. It wasted energy through friction and vibration. It was a slave to fuel chemistry. He asked a radical question: why couldn't the smooth, continuous power of a jet aircraft be scaled down and bolted between the frame rails of an American family car? Hubner's vision was the automotive gas turbine, an engine that uses spinning turbine stages and high-speed gas flow to produce rotational power to turn wheels, rather than producing thrust to fly. Before Hubner's team could build it, they had to solve a staggering physics problem. A jet engine operates at extreme temperatures and constant high RPMs. You could not simply put an aircraft engine in an American driveway. The exhaust gas exiting a pure jet could melt the asphalt at a red light and severely burn anyone standing behind the car. Furthermore, while jet engines were highly efficient at cruising altitude at a constant speed, they were notoriously thirsty when idling. An American driver spent half their time sitting in traffic, waiting at stop signs or idling in the drive-thru. The project began quietly, funded partly by military contracts. During the early 1950s, Chrysler secured a contract with the U.S. Navy to develop a gas turbine for ships. This government funding allowed Hubner to secretly test metallurgical boundaries. They needed exotic materials that could withstand the 1,500-degree Fahrenheit inferno inside the burner, without melting, warping, or tearing themselves apart at thousands of revolutions per minute. By 1954, the secret was out. Chrysler pulled a standard Plymouth Belvedere off the assembly line and replaced its piston engine with a prototype gas turbine. To the untrained eye, it looked like a normal American sedan. But under the hood, there was no radiator, no carburetor, a device that mixes fuel and air before the mixture enters the engine, and no spark plugs. The turbine engine had less than a fifth of the moving parts of a standard V8. When Hübner turned the key, the Belvedere did not rumble. It whined. It sounded like a giant vacuum cleaner spooling up, followed by the distinct, high-pitched rush of a jet on a runway. The 1954 Plymouth Belvedere proved the concept was physically possible, but it was far from practical. The exhaust was still dangerously hot, and the fuel economy was abysmal. But Hübner's team kept pushing. They developed a critical component called a regenerator, a rotating heat exchanger that captured the extreme heat from the exhaust and transferred it back into the incoming compressed air. This did two things. It drastically lowered the temperature of the exhaust exiting the tailpipe, making it safe for pedestrians, and it preheated the air entering the burner, which significantly improved fuel economy. With the regenerator in place, Chrysler was ready for a public spectacle. In March 1956, Hübner and a team of engineers drove a turbine-powered 1956 Plymouth from New York City to Los Angeles. It was a defining moment in American engine history. The car traveled 3,020 miles across the country. It averaged about 13 miles per gallon. Not terrible for a heavy 1950s sedan. But the true shock came at the fuel pumps. The driver did not need highly refined gasoline. The turbine could run on diesel fuel, kerosene, jet fuel, or heating oil. In an era where American mechanics were constantly tuning carburetors to deal with varying grades of gasoline, the turbine simply did not care what it burned, as long as the fuel was combustible and could flow through a pipe. The cross-country trip proved the turbine could survive the American highway. It proved it could climb mountains and endure the heat of the desert. The engine required no oil changes because the oil never came into contact with combustion gases to get dirty. It never needed antifreeze because there was no liquid cooling system to freeze in the winter. But Hübner knew that proving a technology to a group of engineers was very different from handing it over to a normal American driver. The engine still suffered from a noticeable throttle lag, a frustrating delay between the moment the driver pressed the gas pedal and the moment the turbine blades spooled up to deliver torque to the wheels. And while the regenerator helped with heat, building an engine out of aerospace-grade superalloys was astronomically expensive. A cast iron block was cheap to pour and machine. A turbine wheel required precision casting in a vacuum using metals that were usually reserved for fighter jets. The engine had taught Chrysler that a jet-powered car was physically possible. It had not yet solved what would happen when that car met the economic reality of a Detroit assembly line. The cross-country run in 1956 proved the turbine could move a car, but George Hübner knew that an American consumer would never buy an engineering experiment. A production engine could not just work in the hands of a trained technician. It had to work for a tired commuter, a distracted parent, and a driver who ignored maintenance schedules. The engine had to be refined, simplified, and packaged into a machine that felt entirely new. By 1963, inside the Highland Park Engineering Labs, Chrysler finalized the fourth generation of its turbine program, the A831 gas turbine engine. To understand the magnitude of the A831, you have to look under the hood of a standard American car of the early 1960s. The traditional internal combustion V8 was a heavy block of cast iron filled with violently reciprocating parts. It required a radiator to pump liquid coolant through the block to prevent it from melting. It needed a carburetor to mix fuel and air, a distributor to send high-voltage electricity to the spark plugs, and a complex network of belts, valves, and oil pumps. It was a masterpiece of industrial evolution, but it was incredibly complicated. The Chrysler A831 was alien. If you opened the hood in a suburban garage, you did not see a familiar cast iron block. You saw a large aluminum housing that looked like industrial ductwork. The A831 had 80% fewer moving parts than a standard V8. It had no radiator. It had no liquid cooling system at all. It had no distributor, no spark plugs, other than a single igniter used only during startup, and no pistons. The mechanical operation was brutally simple in concept. even if it required aerospace precision to execute. A compressor, a spinning fan at the front of the engine, sucked in air and squeezed it to a high pressure. This compressed air was then forced into a burner, where fuel was sprayed continuously. A single spark ignited the mixture once, and from that moment on, the fire burned continuously, like a blowtorch. The rapidly expanding hot gases blasted through a series of turbine wheels, metal discs with precisely angled blades. The first turbine wheel drove the compressor to keep the engine breathing. The second, entirely separate turbine wheel was connected to a reduction gear, which lowered the massive 4,500 RPM shaft speed down to a usable 4,600 RPM to turn the rear wheels through a modified automatic transmission. This separation of the two turbine wheels was the true breakthrough. It acted as a fluid coupling. It meant the engine could not be stalled. If you locked the brakes and stepped on the gas, the engine would simply spin against the transmission, building torque until the rear tires broke loose. But the A831's most critical engineering triumph was the perfection of the regenerator. Chrysler engineered two massive rotating honeycomb discs made of stainless steel that flanked the engine. As the 1,200-degree exhaust gases exited the turbine, they passed through the rear half of these slow-turning discs, heating the metal. As the discs rotated to the front, the incoming cold compressed air passed through them, absorbing the heat before entering the burner. This genius piece of thermal recycling did two things simultaneously. It drastically reduced the amount of fuel needed to keep the fire burning, and it cooled the exhaust gas to the point that a person could hold their hand behind the tailpipe without being burned. For the American driver, the A831 offered an impenetrable mode of convenience. In the bitter cold of a Michigan winter, a standard V8 required choking, pumping the gas pedal, and waiting for the oil to warm up. The turbine started instantly at 20 degrees below zero, and because there was no liquid coolant to warm up, it delivered hot air to the cabin heater immediately. In the brutal heat of the Arizona desert, the turbine could not boil over because it had no antifreeze. And then there was the maintenance. In 1963, American mechanics made their living on the tune-up, replacing spark plugs, adjusting ignition points, setting ignition timing, and changing dark, contaminated engine oil. The turbine eliminated the tune-up. Because the combustion took place continuously in a separate chamber, the engine oil never came into contact with soot, unburned fuel, or carbon. The oil in a Chrysler turbine remained a clear, golden color indefinitely. But Chrysler faced a manufacturing problem. Detroit assembly lines were built to stamp and weld tens of thousands of identical steel cars a month. They were not equipped to build a short run of highly specialized experimental vehicles. To house the A831, Chrysler contracted Carrozzeria Ghia, an elite Italian coach builder in Turin. Chrysler's head of styling, Elwood Engel, designed a stunning jet-age coupe. It featured a long hood, a vinyl roof, and massive circular taillights that mimicked the exhaust nozzles of a fighter jet. Ghia hand-built 50 of these bodies, painting them in a unique, metallic turbine bronze. They were shipped across the Atlantic to a specialized facility in Detroit, where Chrysler technicians carefully installed the A831 engines, the modified torque flight transmissions, and the aerospace-inspired interiors. By the fall of 1963, the fleet of 50 bronze cars sat waiting. They did not look like laboratory experiments. They looked like the undisputed future of American transportation. The machine was finally ready, but Chrysler now had to find out what would happen when jet-age engineering met the unpredictable reality of the American public. On October 29, 1963, Chrysler officially launched the consumer testing phase of the turbine car program. They did not put the cars in showrooms. They did not sell them to wealthy collectors. Instead, they announced a public evaluation program, asking ordinary Americans to write in if they wanted to drive a jet-powered car for 3 months, completely free of charge. The response was staggering. 30,000 letters poured into Chrysler's headquarters in Highland Park. People begged for the chance to test the future. Chrysler meticulously selected 203 drivers from 130 cities across the country. They were not engineers, mechanics, or professional test drivers. They were a deliberate cross-section of the American public. High school teachers, traveling salesmen, farmers, bank executives, and housewives. Chrysler wanted to know what would happen when an engine born in an aerospace laboratory was subjected to the daily grind of grocery runs, freezing morning commutes, highway road trips, and stop-and-go traffic. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a plane lifted from the runway, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. Chrysler was asking the country to transfer that trust away from the familiar rhythm of a V8 and place it in the continuous fire of a gas turbine. When a driver was selected, the delivery was treated like a state visit. A Chrysler representative would arrive at the family's home, hand over the keys, and give a brief tutorial on how to operate the A831. The starting procedure was simple, but entirely alien to a generation raised on carburetors. You did not pump the gas pedal. You did not feather a choke. You simply turned the key and let go. In a typical American driveway, the sequence was unforgettable. First came the click of the igniter, then a low metallic whine as the starter motor spun the compressor. Within seconds, the continuous combustion ignited, and the engine spooled up to an idle speed of 18,000 to 22,000 RPM. It did not shake the fenders. It did not rumble. It emitted the distinct high-frequency hiss of a commercial jet idling on a tarmac. For the neighbors peering over the fence, it looked like a stylish Italian car, but it sounded like a Boeing 707 waiting for clearance. Once on the road, the turbine fundamentally changed how the driver interacted with the machine. Because there were no pistons changing direction and no violent internal explosions, the engine produced zero vibration. At 60 miles per hour on the newly built interstate highway system, the Chrysler turbine was eerily smooth. Drivers reported that the only sounds they could hear were the wind rushing past the glass and the tires rolling over the pavement. The power delivery was perfectly linear, a single, unbroken surge of thrust that never felt like it was straining. But the greatest spectacle happened at the fuel pump. In the early 1960s, the American gas station was a place of strict routine, dominated by leaded, high-octane gasoline. When a turbine car pulled into a station, crowds instantly gathered. Gas station attendants were often baffled when the driver asked them to fill the tank with diesel fuel, or kerosene, or home heating oil. The engine's multi-fuel capability became a nationwide party trick. Farmers ran the car on tractor fuel. People poured in peanut oil and Chanel No. 5 perfume just to see if it would burn. The most famous demonstration occurred when Chrysler sent a turbine car to Mexico for an international tour. Adolfo López Mateos, the president of Mexico, wanted to test the company's claim that the engine could run on anything combustible. He insisted that the engineers fill the tank with tequila. They did, and the turbine fired up immediately, running perfectly on the liquor, while emitting a sweet alcoholic exhaust note. For a brief shining window in 1964, the engine was not just a prototype. It was a cultural phenomenon. When a bronze Ghia turbine drove through a small Midwestern town, police had to assign escorts just to get the car through the crowds. People followed the cars home from the grocery store. It was the absolute peak of Detroit's jet age optimism, a physical manifestation of a time when American manufacturing believed it could conquer any mechanical limit. The engine had found its believers, and it had seduced the American public. But the industry had not yet shown the price of that future. Between late 1963 and January 1966, the 50 bronze turbine cars accumulated more than 1 million miles on American roads. Chrysler's engineers in Highland Park closely monitored the data, and what they found terrified their traditional competitors. The A831 engine was not fragile. It was practically bulletproof. In Chicago, during one of the most brutal winters of the decade, a test driver left the car parked outside in sub-zero temperatures. Traditional V8 engines across the neighborhood refused to turn over. Their oil thickened to the consistency of molasses, their liquid cooling systems vulnerable to cracked blocks if the antifreeze mixture was wrong. The turbine driver simply turned the key. The igniter fired, the compressor spun, and the engine immediately settled into its 22,000 RPM idle, blowing instantly hot air into the cabin heater. There was no choke to feather, no engine block to warm up, and no radiator to freeze. In the Deep South, drivers pushed the cars through sweltering 100-degree summers in heavy traffic, while piston engine cars sat on the shoulder of the highway with boiling radiators and hissing steam. The turbine car remained completely unaffected. It could not boil over because it contained no water. The maintenance logs returned to Detroit were even more shocking. When the cars were brought back to Chrysler service centers for inspection, mechanics found that the engine oil, which was only used to lubricate the reduction gears and accessory drives, was perfectly clean. Because there were no pistons and the combustion took place in a sealed burner, there was no carbon buildup. Because there was no conventional ignition system, there were no spark plugs to foul or distributor points to replace. When a turbine test driver pulled into a neighborhood repair shop for something as simple as a tire rotation or a brake adjustment, mechanics would drop their wrenches and crowd around the open hood. There was no heavy cast iron block to inspect. There were no valves to adjust. The engine bay looked like industrial ductwork. For an American machinist used to measuring cylinder bore and piston ring gaps, the turbine was a sealed mystery of aerospace-grade superalloys. The American tune-up, an entire economy of neighborhood repair shops, service manuals, and parts counters, was suddenly threatened with obsolescence. This was the true power of the program. Chrysler had not just built a fast car, they had built an appliance that removed the mechanical friction of ownership. In 1964, at the New York World's Fair, Chrysler displayed a turbine car on a massive rotating pedestal. Millions of Americans walked past it, looking at a machine that promised to sever the country's absolute reliance on high-octane gasoline. It was the peak of industrial pride, a moment when Detroit felt invincible enough to rewrite the laws of thermodynamics for the American highway. But a machine is never evaluated in a vacuum. It is judged by how it fits into the world already built around it, and the data from the 203 families revealed the first hidden costs of jet-age power. The people who drove the turbine cars loved the smoothness, the sound, and the novelty of fueling up from a kerosene pump. But they also reported a frustrating flaw. When a driver was sitting at a red light and the light turned green, they would step on the gas pedal. For 1 or 2 long, agonizing seconds, nothing happened. This was throttle lag. The compressor and turbine wheels needed time to spool up from their 22,000 RPM idle to their maximum operating speed of 500 RPM before they could deliver torque to the transmission. In a society accustomed to the instant, tire-chirping response of a Detroit V8, that 2-second delay felt like an eternity, especially when trying to merge onto a busy freeway. Then there was the fuel gauge. While the turbine was reasonably efficient at 60 miles per hour on the open road, it was ferociously thirsty when sitting still. An internal combustion engine can idle efficiently at 600 RPM. A gas turbine must maintain a massive fire and tens of thousands of revolutions just to keep itself running. In city traffic, the turbine car consumed fuel at an alarming rate. The machine was a triumph of engineering, and it had captured the imagination of the country. But the real world was about to enforce a brutal new reality of manufacturing costs, fuel economics, and clean air laws that the turbine had never been designed to survive. The first crack in the Chrysler turbine empire was not a catastrophic mechanical failure. It was a slight hesitation, a pause between a driver's foot hitting the floorboard and the car actually moving forward. When the 203 families returned their bronze Ghia cars to Chrysler at the end of the public evaluation program in January 1966, the data confirmed that the A831 engine was incredibly reliable. But it also revealed the friction between aerospace engineering and the reality of the American commute. When a driver tried to merge onto a busy interstate or dart across a crowded intersection, they stepped on the gas pedal and waited. For 1 to 2 seconds, the engine had to spool up from its 22,000 RPM idle to its 44,500 RPM operating speed. In a commercial jet, a 2-second delay on a runway was irrelevant. In an American car, where a driver was accustomed to the instant, tire-chirping torque of a V8, that lag felt dangerous. The second crack was hidden in the fuel bills. While the turbine was relatively efficient on a long highway trip, it was ferociously thirsty in the city. An internal combustion engine can sit at a red light idling efficiently at 600 RPM. A gas turbine must maintain a massive fire and tens of thousands of revolutions just to keep itself running. In the stop-and-go traffic of a suburban rush hour, the turbine car consumed fuel at an alarming rate. But George Hubner and his engineering team believed these were solvable problems. They returned to the Highland Park labs and began developing the 6th generation of the engine, aiming for a full production rollout in a Dodge Charger or Coronet by the late 1960s. That was when the engine ran headfirst into the brutal reality of Detroit manufacturing economics. Force 1, iron, aluminum, fuel, and manufacturing costs, was the invisible wall that experimental engines rarely survive. In a traditional Detroit foundry, casting a V8 block, the main engine structure that holds the cylinders, was a brutal but perfectly understood science. You poured molten iron into sand molds, let it cool, and machined the cylinder bores. It was heavy, but it was cheap, and American factories could produce tens of thousands of them a month. The turbine engine played by different thermodynamic rules. The turbine wheels, the spinning discs of metal blades that extracted power from the 1500-degree exhaust stream, operated in a perpetual hurricane of fire. Cast iron would warp and melt in seconds under those conditions. The blades had to be made from exotic superalloys, the kind of high-temperature metals used in military jet engines. Chrysler's metallurgists brilliantly invented their own cheaper iron-based alloy, called CRM6D, to avoid using expensive aerospace cobalt. But even with a cheaper material, the manufacturing process was agonizingly slow. You could not simply pour a turbine wheel in a sand mold. It required precision investment casting, often in a vacuum, to ensure the blades were perfectly balanced. If a turbine wheel was slightly out of balance at 40 now and 500 RPM, it would tear the engine apart. Chrysler executives looked at the math. The turbine was brilliant, but it was incredibly expensive to build at scale. To justify the tooling costs, they would have to sell the cars at a massive premium or completely overhaul their factory lines. And while the accountants were looking at the foundries, the federal government was looking at the tailpipe. Force 3, regulation, emissions, and fuel economy fundamentally changed the design problem for every engine maker in America. In the late 1960s and early 1970s, the Environmental Protection Agency began drafting the Clean Air Act, targeting the smog that was choking cities like Los Angeles. At first, Chrysler's engineers thought the turbine was their silver bullet. Because the engine burned its fuel continuously and completely, its exhaust was incredibly clean when it came to unburned hydrocarbons and carbon monoxide. In a standard V8, unburned fuel was a constant problem, requiring complex emission systems, equipment designed to reduce pollutants from engine exhaust, like early catalytic converters. The turbine didn't need them, but there was a trap hidden in the extreme heat of the burner. When you compress air and burn it at 1,500 degrees Fahrenheit, the intense temperatures cause the nitrogen and oxygen in the air to fuse together, creating nitrogen oxides, or NOx. NOx was the primary chemical responsible for the thick, brown smog hanging over American cities, and the EPA was determined to regulate it out of existence. To lower NOx emissions, an engineer must lower the peak combustion temperature. But a gas turbine's entire efficiency relies on keeping those temperatures as high as physically possible. If Chrysler lowered the heat in the burner to please the EPA, the engine's already fragile fuel economy would collapse. If they kept the heat high to maintain efficiency, the engine would be illegal to sell. The engineers were caught in a thermodynamic paradox. They designed complex variable geometry nozzles and new burner tubes to try to satisfy the government, but the target kept moving. Every time they solved one emissions standard, a stricter one was passed. The engine that was designed to conquer the 1960s was suddenly forced to survive the 1970s, and the world outside the laboratory was about to become much more hostile. While Chrysler's engineers wrestled with the nitrogen oxide paradox in their testing labs, the world outside was preparing a much more brutal test. Force 4, fuel, oil, supply chains, and energy shocks arrived in October 1973. The Organization of Arab Petroleum Exporting Countries proclaimed an oil embargo. Almost overnight, the American relationship with fuel changed from a casual assumption of endless supply to a state of national panic. Gas stations ran dry. Cars lined up for blocks. The price of a gallon of gasoline quadrupled. Suddenly, the turbine's poor city fuel economy was no longer just an engineering quirk. It was a fatal flaw. The original promise of the A831 engine was its multi-fuel capability. It could run on diesel, kerosene, or home heating oil. But in the 1973 energy crisis, the cost of all petroleum products skyrocketed. An American consumer did not care if a car could burn furnace oil if they could not afford to heat their house in the first place. The market no longer wanted a smooth, multi-fuel jet engine that drank heavily at a red light. The market suddenly demanded small, highly efficient, four-cylinder internal combustion engines, compact power plants that could sip fuel in heavy traffic. But George Hubner and his dedicated team refused to let the dream die. They believed that with enough time and funding, they could miniaturize the technology and solve the fuel consumption problem. Throughout the 1970s, Chrysler developed a sixth and then a seventh generation of the gas turbine engine. They installed these newer, smaller turbines into standard mid-size production cars, like the Dodge Aspen and the Chrysler LeBaron. These late 1970s turbine cars were engineering marvels. They ran at even higher temperatures to improve efficiency, utilizing new ceramic components that could survive the intense heat of the burner better than metal alloys. But the world they were built for no longer existed. The jet age optimism of 1964, when Americans believed technology could conquer any boundary, had been replaced by the grim economic reality of the late 1970s. Force 6, corporate consolidation and financial survival, delivered the final blow. By 1979, the Chrysler Corporation was bleeding cash. The company's traditional V8 cars were not selling. Their manufacturing quality had plummeted, and they were on the verge of total bankruptcy. To save the company and prevent the loss of tens of thousands of Detroit manufacturing jobs, Chrysler's new CEO, Lee Iacocca, went to Washington, D.C. to ask the federal government for a massive bailout in the form of loan guarantees. The government agreed to save Chrysler, but it came with merciless conditions. The United States Treasury and the Loan Guarantee Board looked deep into Chrysler's books. They demanded that the company abandon high-risk, futuristic research and focus entirely on building cheap, practical, front-wheel drive cars powered by economical four-cylinder engines. They demanded the K-car. The turbine engine program, which had consumed millions of dollars and decades of research, was viewed by Washington bureaucrats as an expensive, indulgent fantasy. To secure the bailout money that would keep the Detroit assembly lines moving, Chrysler was ordered to kill the turbine. In April 1981, after 27 years of continuous research, millions of test miles, and some of the most brilliant metallurgical engineering in American history, Chrysler officially shut down its gas turbine engine program. The engineers packed up their notes. The ceramic turbine wheels were put into boxes. The specialized testing labs in Highland Park went silent. The engine still ran. The throttle lag remained. The emissions rules tightened. The fuel prices spiked. The government demanded a safe bet. The funding stopped. The jet age dream was over. The machine was dead, leaving only the physical proof that it had ever existed. In the aftermath of the program's cancellation, the Chrysler Corporation faced a brutal legal and financial reality. The 50 Ghia-bodied turbine cars had never been legally imported into the United States for permanent sale. They were brought in under a temporary bond for testing purposes. If Chrysler kept them, they would owe a massive tax bill on custom Italian coachwork that was suddenly useless to their new, austere corporate direction. Worse, their legal department was terrified of the liability of selling experimental jet cars to the general public. The order was given to destroy them. In a Detroit scrapyard, as the public watched in dismay, 46 of the most advanced automobiles in the world were fed into a car crusher. The bronze paint, the aerospace-inspired interiors, the intricate stainless steel regenerators, and the cast superalloy turbine wheels were reduced to jagged cubes of scrap metal. But Chrysler did not destroy all of them. Executives and engineers managed to save 9 cars from the crusher. They deactivated the engines in most of them, removing the critical fan blades or sealing the burners, and quietly donated them to museums across the country, ensuring that the government could not tax them and the public could not drive them. Today, those surviving cars form a scattered, silent preservation community. You can find them resting under the soft lights of the Henry Ford Museum in Dearborn, Michigan, the Smithsonian in Washington, D.C., and the Peterson Automotive Museum in Los Angeles. Only a handful of these cars remain fully operational. One belongs to the Chrysler Historical Collection. Another sits in the private garage of television host and collector Jay Leno, who purchased it and kept the A831 engine perfectly tuned, periodically taking it out onto the streets of Southern California, where it still emits that unmistakable high-pitched vacuum whine of a Boeing 707 idling at a stoplight. But the legacy of the Chrysler turbine car is not about nostalgia for a lost shape or a vintage sound. It must pass the test of industrial memory. The surviving cars are not just beautiful oddities. They are physical arguments about a time when American manufacturing was willing to take a colossal existential risk. In the modern era, the automotive industry is undergoing another fundamental shift, moving away from the internal combustion engine toward electrification, battery power, and hybrid systems. The transition is often framed as an unprecedented leap into the unknown. But the Chrysler turbine proves that the American auto industry has stood at the edge of this exact cliff before. In 1963, George Hubner and his engineering team did not just try to make a better car. They tried to eliminate the piston, the spark plug, the radiator, and the oil change. They tried to break the American driver's absolute dependence on high-octane gasoline, proving that a car could run on diesel, kerosene, furnace oil, or even peanut oil. They tried to replace the violent, reciprocating explosions of the V8 with the smooth, continuous fire of a gas turbine. The technology did not fail because it was mechanically unsound. The A831 was reliable, smooth, and famously durable in the extreme cold. The technology failed because an engine does not live in a vacuum. It lives in a system, and the system changed. The Clean Air Act demanded lower nitrogen oxides, forcing the engineers to lower the combustion temperatures that the turbine needed for efficiency. The 1973 oil embargo destroyed the appeal of an engine that drank heavily in city traffic. And finally, the financial collapse of the Chrysler Corporation forced the government to demand safe, predictable, four-cylinder economy cars in exchange for bailout money. The machine was brilliant. The economics and the regulations around it were fatal. The surprise footnote of the turbine empire is how long the engineers refused to surrender. While the public remembers the glamorous bronze Ghia cars of 1963, they forget that Chrysler kept developing the engine in secret for almost 2 more decades. They built a 6th and 7th generation. They put them in mundane Dodge Aspens and Chrysler LeBarons. They experimented with advanced ceramics that could withstand temperatures that would turn cast iron into a puddle. They fought the EPA, the oil shocks, and their own accountants right up until the federal government forced them to lock the laboratory doors in 1981. America did not stop needing power. It simply stopped needing that kind of power. The market demanded efficiency over ambition and chemistry over thermodynamics. Today, the Highland Park engineering facility, where the A831 was developed, has been largely abandoned, its testing cells quiet, its metallurgical breakthroughs absorbed into history. The American highway is still dominated by the very same piston engines that George Hubner tried to render obsolete over 60 years ago. Somewhere in an American museum, a bronze Chrysler turbine car sits silent under the display lights, its massive jet-inspired tail lights reflecting the room, the intricate turbine wheels locked in place, waiting for a key to be turned and a fuel to be burned that will never come again. See you in the next video.